Lesson 40 activity. In the diagram at right, the areas of regions 1, 2, and 3 are 4, 10, and 7 respectively. 4, 10, 7. And we're going to evaluate the following integrals. So the first one is the integral from 0 to a. And so that is just the 4, that's region 1. From a to b, that's from a to b, that's the 10, except it's an integral, so it's a signed area, so it's negative 10. And then from b to c, that's 7, and it's above the axis, so that's positive. From 0 to b, that's a positive 4, but a negative 10. Altogether, it's a negative 6. We're adding those up, including the signs. From a to c, that's a negative 10 and a positive 7, negative 3. From 0 to c, that's the whole thing. Positive 4, negative 10, positive 7. Altogether, it's a positive 1. Okay, from a to 0. Now this has gone like, quote, backwards from what you might expect. So what you really want to do is consider the integral from 0 to a, and then whatever you get, you change the sign. But the integral from 0 to a we've already done. We got 4. That means that the integral from a to 0 is the same number, but opposite sign. Same deal here. Integral from b to a is, quote, backwards. So you think about the integral from a to b, which we did up here. We got negative 10, so this integral must be the opposite sign. Same number, opposite sign. And then c to a, we're going to find the integral from a to c. I see it right here. We got negative 3 for that one, so this must be the opposite sign. Same number, positive 3. Here's a multiple choice AP question. We're given that the integral from 1 to 10 is 4, and the integral from 10 to 3 is 7, and we're trying to find the integral from 1 to 3. Let's take a look at these numbers. I've got a 1 here. I've got a 10 here. I've got another 10 here, and then I've got a 3 over here. So far I've seen 3 different numbers, 1, 10, and 3. But then on the thing we're trying to find, we're looking for the 1. We've seen that one before, all the way up to 3, and we've seen that one before. So it's actually the same 3 numbers over and over again. So I will point us in the right direction here. I know that if I did the integral from 1 to 3, and I added the integral from 3 to 10, then I would get exactly the same thing as not stopping in the intermediate spot at 3, but really just going a straight shot from 1 over to 10. So this is the fact that I'm trying to use. Some of these things I already have. The integral from 1 to 10, that's just a 4. I'm going to plop that right there when I have all 3 pieces, or 2 of the 3 pieces. Okay, integral from 10 to 3, well, that's kind of like this integral, but it's actually the wrong sign. So that means that the integral from 3 to 10, the order that I'm thinking of is actually this number, but the opposite sign. So it's really just the negative 7. So I think I now have 2 of the 3 pieces, and I'm ready to start plugging in. So putting these 3 things together, the integral from 1 to 3 is what we're after. I'll copy that. Plus, the integral from 3 to 10 is the opposite of that 7 number that we see over there, so that's a negative 7, equals the integral from 1 to 10 is given as 4. So that means that the integral I want, by adding 7 to both sides, is 11. Okay, 3 talks about properties of symmetry. If f is even, like in this picture here, then the integral from minus a to a, I'm just making up something, but you just got to pick the 2 points that are symmetric over the y-axis. So the total area, this total combined red area, is really just double one of those red pieces because of the symmetry, right? The area of the left-hand one is the same as the area of the right-hand one. So it's really just 2 times the integral from 0 to a of f of t dt. Okay, if f is odd, like in this picture, and we want the integral from negative a to a, so I'll just pick negative a there, and then the corresponding positive a here. So we've got this area down here, and then this area up here. Now clearly those 2 green areas are the same, except the part that's below the x-axis is treated like a negative in the integral, and the part that's above is treated like a positive. And so they cancel completely. And for any odd function, if you do the integral from minus a to a, you get nothing. Another application of integrals is to find the area between 2 curves. Consider f of x equals x squared. So that's this one. And g of x equals the square root of x. And we're going to shade in the area between these two curves. And we're looking for an area that is completely closed in. So even though there's area up here, that goes unbounded forever. That is not what we're talking about. We are talking about a finite finite boundary, finite area. It's also not this over here because that has nothing to do with this curve. So the area between the two curves for sure is that. It says find the coordinates of the points of intersection. Don't guess, but use algebra. It sure looks like it's x equals 0 and x equals 1, but we're not going to guess. We're going to use algebra. So I know for sure that the y values are the same at those 2 points. So that means that x squared has to equal the square root of x. Let's square both sides. So x to the 4th equals x. Let's get one side to 0 by subtracting x. Let's factor out the greatest common factor on the left. X comes out of both. Let's set each of these factors equal to 0. Either x equals 0, hey, that's one solution, that's one point of intersection, or x cubed minus 1 equals 0. Add the 1, and then take a cube root of both sides. And of course, the cube root of 1 is just 1. So yeah, just like the picture looks, the x coordinates are 0 and 1. But now we can say that using algebra. Let's write an expression with two integrals that represents the area of the shaded region. All right, here we go. I want the area of the blue, but an integral gives you the area not between two curves, but rather between a curve and the x-axis. So for example, suppose that I want the area here underneath that x squared curve. So if I want an integral to represent that area, then we would say the integral from 0 to 1, those are the x coordinates of the points of intersection. That's why we needed them. Underneath the x squared curve. So x squared goes right here, dx. Actually, I'm going to change the colors of these. Okay, now suppose that we were to calculate the area underneath the square root of x function. It's going to be hard to see because I'm going to have stuff overlapping, but it's the area inside of that wedge-shaped thing. So that total area there, orange, is the integral. Again, 0 to 1, those are the points of intersection, the x coordinates. And then the function here is square root of x. Okay, but I actually didn't want either of those areas. What I wanted was the area between the two curves. So what I want is this space right in here going up to there. And so is there a simple thing I can do with the orange area and the green area to get just the blue area? Sure, we just need to subtract these two things. So we're subtracting the bigger one minus the smaller one. So in this case, it's square root of x1 minus the square root. That's going to give me the area between the curves. And then part D says rewrite the answer from part C as a single integral. Well, hey, we had this nice integral property that said if you have a single integral with a subtraction, some function minus some function, you could split it up as some function minus integral some other function. Well, this is just going the other direction. We currently have two integrals being subtracted. Here they are, two integrals being subtracted. We're going to rewrite that as a single integral with subtraction inside. So here we go. Square root of x there, x squared here, subtract in the right order. Technically, we need parentheses here because they both have to be attached to that dx, 0 to 1. And that's how we represent the area between those two curves with a single integral. And so for future problems like this, where you're trying to find the area between two curves, I'd actually really like you to go straight to this single integral subtraction answer as opposed to writing two separate integrals. How do you know which one goes first? It's the one that's on top. That has to go first. So the square root function was above the square function for the region we were talking about. So it was just integral of the square root of x minus the x squared. And again, we needed the points of intersection. Okay, type the answer from part D into a graphing calculator to find the area of the shaded region and round. Okay, we can do that. Math 9. So remember, this one was the square root function first. minus the x squared, comma, x, comma, 0, comma, 1. So it turns out the area there is roughly 0.3 repeating. Now remember, the calculator is approximating here. I actually think that the area is exactly 0.3 repeating, which is kind of odd that it would be such a nice number. Sure looked like it was 1/3. That the orange area is the area of a strange curvy shape, and the green area is the area of a different strange curvy shape. But somehow when we subtract these two, neither of which we expect to be nice, we get a nice number, 1/3. Number 5, suppose we want to find the integral from 0 to 4 of 4t cubed dt, but we don't have our favorite ti product on the stranded desert island on which we find ourselves. Now we've already seen the fundamental theorem, which said that the integral of f prime of t dt from a to b is really f of b minus f of a. Again, notice it's a prime here and not here or here. So we can imagine if we want to find this integral, we can kind of force it to be in this form, right? And so we're imagining 4t cubed is f prime of t for some function f. And so we're going to try to come up with that function to help us understand, help us get this integral. So here we go. F prime of t is 4t cubed. We're trying to force that, and therefore f of t equals, so we're just trying to think, somebody took the derivative of a function and got 4t cubed. Not taking the derivative of 4t cubed, that's not what we're trying to do. We're trying to do the other direction. Somebody took a derivative of something and got 4t cubed. We need to undo what they did. 4t cubed, what did it come from? It came from t to the 4. And if you check, the derivative of t to the 4 is 4t cubed. I said this in another video recently, but there's actually infinitely many answers. Instead of t to the 4th, you could do, for example, t to the 4th minus 36, and that would also work. We're just going to do t to the 4th right now. And so now we're going to use our fundamental theorem to evaluate this integral. Integral 0 to 4 of 4t cubed dt is equal to f of 4 minus f of 0. Remember, it's always top minus bottom. But f of 4 we can now calculate because we know that f of t is just t to the 4th. So this is 4 to the 4th minus f of 0. We can do that too. That's 0 to the 4th. And so that means that the integral that we wanted is actually just 4 to the 4th, 256 minus nothing. And so we got that without doing any kind of crazy areas, right? The area underneath this curve is, I don't know how to calculate it other than what we just did there or using a calculator. So we didn't need a calculator here, but we'll use one just to make sure that we see that we got it right. There's 4t cubed, comma, x, comma, 0, comma, 4. I did not do that right. Comma, 4. And we got exactly 256.